Let's start. And I will say these squiggles on the board are for the camera. They're because if we don't have something on this whiteboard for the camera to focus on, it focuses in and out. So this is its cue, the camera's cue. We're going to start here with water. We all know that water is H2O. And this is telling us that each water molecule is composed of 2 atoms of hydrogen and 1 atom of oxygen. The atomic weight of oxygen is 16. The atomic weight of hydrogen is 1. This gives us a total of 18, since there are 2 hydrogen and 1 oxygen. So we have a molecular weight of water being 18. Well, we can do a similar sort of calculation if we think about nitrogen. Again, some 79% of the air around us is nitrogen. The nitrogen is composed of 2 nitrogen atoms linked by a covalent bond. Because there are 2 nitrogens, each one of which has an atomic weight of 14, the molecular weight of nitrogen is 28. Similarly, over here, we're going to talk about oxygen. Oxygen has an atomic weight of 16. There are 2 of them. Gives us a molecular weight of 32. And again, the 2 oxygen atoms are linked by a covalent bond. In these covalent bonds, the electrons are shared. There is no unequal distribution of electrons in this molecule. The electrons in the oxygen, this oxygen atom and this oxygen atom, share these electrons equally, such that the electrons spend as much time around this oxygen as this oxygen. Because of that, this molecule does not have any charge to it. It's neutrally charged. And if we cool it down, we find that its boiling point is minus 183 degrees centigrade. Now, don't memorize these numbers, but I'll use them to illustrate an idea. The same is true for nitrogen. The electrons in nitrogen are equally shared. There's no endedness to this molecule. There's no charge greater on one end than the other. And because of that, because there's no endedness, these molecules of nitrogen act independently of one another. In order to get this nitrogen to become liquid, we have to cool it to minus 196 degrees centigrade. That's the boiling point of nitrogen. Again, these are extremely cold temperatures. These are, remember, minus 272 degrees centigrade is absolute zero. So these are mighty cold. Water, on the other hand, and we all know this intuitively, water boils. The boiling point for water is 100 degrees centigrade at sea level. The freezing point for water is 0 degrees centigrade. So what is it about water that makes these physical characteristics so remarkably different from nitrogen and oxygen, even though both nitrogen and oxygen have greater molecular weights? The answer to that question comes from something known as the dipole moment structure of water. So we'll take this portion of the panel and describe this as the dipole moment in water. The long and the short of this is the dipole moment in water arises because the electrons in this molecule are not equally shared. it's true that the overall charge on water is neutral. But we'll find that because of the peculiar characteristics of the oxygen atom and the hydrogen atoms, that these molecules unequally share their charge. So let's think about that for a moment. So here is an oxygen. Covalently linked to that oxygen will be a hydrogen and a hydrogen. Therefore, H2O. Now, you may remember from your chemistry that what a hydrogen is simply a proton and a single electron that's orbiting around that proton. It's really tiny. Whereas oxygen is a considerably more massive kind of molecule. What happens here is that the electrons are borrowed by the oxygen in such a way that the electrons tend to spend more of their time around the oxygens than they do around the hydrogens. You can think of the mass of the oxygen as borrowing these electrons. Now, Heisenberg tells us we don't know exactly where those electrons are, but he also tells us that they're someplace in this cloud. And he also says that in water, these electrons will spend a greater amount of their time out here around the oxygen than they will around the hydrogens. We say then that this end of the water molecule has a partial, this is a delta, negative charge to it. Now recall that these hydrogens are simply a proton with an electron around them, and that this electron has been borrowed, spends more time around the oxygen than around the hydrogens. That imparts to this end of the hydrogen a partial positive charge. This difference in charge on the different ends of the water molecule is said to be the dipole moment. This has enormous implications for how biology functions in our world. Because think about this water molecule as having a magnet up here that's, say, a south pole, and having two magnets down here that, say, are north poles. They're oppositely charged. In other words, this negative is going to attract to a positive. It will be attracted to a positive. So now imagine we have over here another water molecule. This water molecule, again, has the oxygen. It has its two hydrogens. The oxygen has the partial negative. The two hydrogens have their partial positive. The partial negative end on the oxygen will be attracted to this partial positive on the neighboring water. This will form a bond. This is a kind of bond that results because of the charge on the oxygen and the hydrogen. This is said to be a hydrogen bond. The hydrogen bond is now going to occur down here with another oxygen. And this negative one up here is going to be attracted to a hydrogen with an oxygen. So you now begin to see how these water molecules, through their hydrogen bonding, can interact one with another. Now, it's true that these interactions in liquid water are remarkably fleeting. No more than a nanosecond, probably down around picoseconds. So these two molecules will interact. This molecule will switch. It will find another water molecule to interact with. This one will switch around and find another water molecule to interact with. But these guys are held together by the electromagnetic attraction between the negative and positive ends on the water. That's the reason these water molecules can stay together and remain liquid at temperatures between 0 and 100 degrees, whereas molecules such as nitrogen and oxygen, which don't have that uneven distribution of charge, require a much, much colder temperature to become liquid. But these guys will remain liquid across a broad range. And in fact, to finish this story, think about ice. We know that once you cool water at standard temperature and pressure to 0 degrees centigrade, that now ice will form. Ice forms because of the same interaction. Ice forms a kind of crystal because of the interaction with the negative and positive ends of the molecule. But it turns out water is again peculiar when it freezes. It's peculiar such that the distances, the average distance between the negative end on one molecule and the positive charge on a neighboring molecule, these hydrogen bond lengths actually get larger when the crystal forms and forms ice. Because these bond lengths are somewhat greater in ice than they are in liquid water, the density of ice is somewhat less than water. It's the reason icebergs float in the ocean. It's the reason when you drop an ice cube into your drink, it floats to the top, because of the expansion of this molecule when that crystal structure forms. And there are actually fewer molecules of water in a cubic centimeter of ice than there are in a cubic centimeter of water. Yes? Is water the only molecule that does this? There are a few organic molecules that you can make that will do this, but they're really, really rare. Almost all of the others will basically get smaller and smaller and smaller when they come together and freeze into either a liquid or even or liquefy and then freeze, will actually get smaller. Water is really weird. And any of you who've taken ecology courses will notice this too. The water actually reaches its greatest density at 4 degrees centigrade. And this has real implications for lakes, because it means that as the water cools in the winter and reaches a maximum density at 4 degrees, it sinks to the bottom, and all that water in a lake will turn over until it freezes at the top, and you get that floating ice at the top. But again, it's unusual. But we all live with this problem. Any of you who have had your pipes freeze at home know the forces that could be generated by ice. They'll break those pipes in no time simply because of the forces generated, that when the water freezes, crystals form and the bond length, the hydrogen bond, actually gets longer. Let me show you a couple of pictures of this. So this is simply a scale model of what I drew on the board. And then we've switched the colors. But nonetheless, it shows the partial negative charge on this end of the oxygen. And because the electrons have been borrowed, the partial positive charges out on the hydrogens. There is a particular, I think it's 104 degrees, because this is a tetrahedral molecule, where these hydrogens are coming off the oxygen. But again, the major idea we want to emphasize is this difference in charge in different parts of the molecule. And this then gives rise to this concept of the water molecules interacting one with another in liquid, such that we have these hydrogen bonds. Now, this is frozen in time. In reality, the time that this water molecule would spend interacting with this water molecule would be maybe picoseconds to nanoseconds, very short period of time. But nonetheless, as soon as this one turns around, it's going to find another water molecule to interact with. And so that's the reason the water will remain liquid. There's one final idea I want to emphasize about this interaction of water molecules. And this is something that we're all familiar with. So let me go up to the upper panel. And what I'm going to talk about here for a little bit is the idea of hydrogen bonding and surface tension. We're all familiar with surface tension in one form or another. But what I want to do is try to tie together the concepts that we described in the upper board, this idea of hydrogen bonding, with what happens with water at the air-water interface.